Hi, this is David Van Vranken here at UC Irvine. I want to welcome you to our 23rd lecture here in the Chemistry 51C series. We just had our second midterm on Friday, and I want to tell the class, great job. The scores were better than last time. You guys did great. The mean was 64.4 versus about 60 last time, so keep those scores going up. We got one more midterm coming up. I just want to tell you to keep working hard and working problems and practicing organic chemistry at every chance you get. If you've been pouring energy into our class and it just feels like it is not paying off, I totally see where you're coming from. And I saw this article, or a link to this article, a couple of years ago, and I noted it down. And it was by Kim Shandro at Entrepreneur Magazine. The article is titled, "This is what Bill Gates says makes him feel powerless." And what does it take to make a man who is worth $98 billion, the second richest man on the planet Earth, only because he's been giving his money away hand over fist? What does that take? Well, when you look in the article, it came from a Reddit Ask Me Anything session that Gates did. And he responded to some of the things that stress him out. One of them was terrorists. The other was staying up too late at night reading books. But the other was his recollections of his time at Harvard. And what he notes that the big exception for all the A's that he got was organic chemistry, where he ended up making a C+ in the course. When you're as powerful as Bill Gates, years later, to come back and recall this issue of organic chemistry and how tough it was, I can imagine how you feel. I've been in your position where you just throw everything you've got at a course and it doesn't seem to click. It wasn't clear to me whether this is just some reflection of somebody who's growing old and looking back wistfully. And when I looked back at this issue, it turns out that he's been talking about this not just in the recent past, but going back in time. Here's an article that was published in New York Times Magazine about a conversation between Professor David Christian, a historian at San Diego State University, and Bill Gates. And he says, "I'm pretty sure, I'd have to double check my transcript. I think I never, ever got a B ever at Harvard. I got a C+ and I got A's. And what was that C+ in? It was in organic chemistry." I got interested. Who was this person who gave him a C+? I tried looking on the web. It's a small community. Everybody knows each other just for laughs. But I couldn't find that information. But what I did find was an article back in 1997. So over 20 years ago, over 2 decades ago, this was still a subject on his mind, where Bill Gates talks about the worst class I ever took was introductory organic chemistry. For a person who has reached these heights to still be influenced and still have these feelings, this angst over organic chemistry, it really puts things into perspective. And it makes me think, what if he had gotten an A in organic chemistry? Maybe he would have gone into organic chemistry or biochemistry or medicine, and think of what the world would have been deprived of. I feel like sometimes I see people on campus that I vaguely recognize, and I think maybe that was a person in my class, and maybe they just don't feel comfortable saying hi to me, or maybe you might think I'm going to ask you about your grade. I would never do that. Our relationship is more than just you getting a grade in this course. You are more than your grade in this organic chemistry course. This course does not define you. It does not define your future. We have a shared relationship where I'm teaching the class and you're taking the class. Let's celebrate that relationship. But please don't allow yourself to think that I in any way judge you for your grade in this class. You guys are all awesome and you've made it so far to get here. Great job. Keep on studying. Don't let this class define you, whether you do good or bad. Go off and do great things. And it can be anything. It doesn't have to be the chairman and CEO of Microsoft Corporation. There's so many ways to make an impact on people's lives. Great job, and keep going with that. So we left off on, I think it was on last Wednesday, before the exam, talking about the chemistry of amines and protonation. And I mentioned the fact that generally what the the equations that govern equilibrium of amines and protonation are really simple equilibria for most organic chemistry reactions, where you're dumping stuff into a flask and you're allowing different species to compete for protonation. I think all of you have heard of the Henderson-Hasselbalch equation, which is for buffered conditions like human blood or the cytosol of cells. And there you use the Henderson-Hasselbalch equation to allow you to tell what fraction of your species are protonated when somebody tells you the pH. So let's go ahead and talk a little bit more about this idea of protonation of amines and this equilibrium between protonated charged amines and neutral amines. This is closely connected to the solubility of those species. So these types of questions tend to be important for all kinds of standardized exams, MCAT, the PCAT, the DAT, the OAT for optometry school. And the reason is this has a lot to do with drugs and their solubility and their ability to get inside of cells and across biological membranes. But I'm going to paint this in a scenario where we're talking about organic reactions and working up organic reactions. If I take a typical amine and I partition it between ether or some other organic solvent, doesn't matter, and an aqueous acid solution. So I'll take a cyclic amine called piperidine. This is a super common organic base or organic amine. If you put this into a mixture of ether and aqueous hydrochloric acid, it's going to be protonated. If you shake up this mixture and make an intimate kind of mixture, it will then separate like oil and water does, and the amine will end up in the organic in the aqueous phase, even if it starts in the ether phase, because once it's protonated, it will get pulled completely into the aqueous phase. Now, in contrast, if I take that same amine, whether it's got the proton on there or not, and I partition it between an organic solvent and aqueous base like sodium hydroxide, not buffered conditions. We're just talking about 1 molar sodium hydroxide. It's not buffered at all. There's just excess base in there and strong base. Now, that would be, let me not even draw it there in the organic phase. Now it would be deprotonated and neutral. And neutral organic molecules like to go into organic solvents. And it's this property, the ability to protonate and keep things water soluble and deprotonate and get things to go into organic solvents that makes amines good drugs. Because once you deprotonate them and they're neutral, they can go across biological membranes like cell membranes, blood-brain barrier. There's all kinds of membranes inside the human body where this ability to be neutral and unprotonated gives it that capacity to cross through membranes. Okay, so so you need to know this idea of partitioning. Acids, amines are protonated and charged, that's water soluble. And then in the presence of base, they're deprotonated, not to make an anion. There's no way you could make an amide anion using sodium hydroxide. The only base that can deprotonate and make an N- amide anion is butyllithium. Of course, you couldn't have that in water. You might have been using this in the past, I hope not. But this is exactly the chemistry that cocaine addicts use when they freebase cocaine. So if you go to your supplier and you buy that nice white powder, that's the hydrochloride salt of cocaine. Cocaine has an ammonium group on there, and a lot of salts tend to be nice white free-flowing powders. But if you want to get this to cross biological membranes like the one in your nasal membrane, if you were to snort or inhale that, you've got to get rid of that proton. And so what people do is they mix this with baking soda, sodium bicarbonate, which then acts as a base to pull off that proton from the amine. It's not a good base. You have to heat this with a flame or some pretty intense heat source. And what that does is it deprotonates the amine, and then you lose carbon dioxide and you lose water. And then the sodium from the sodium bicarbonate mixes with the chloride and generates sodium chloride salt. And then you snort this and it just flies across those membranes in your nasal passages, go right to the brain, and so you get this incredible high. And so the free base of cocaine, often sold as crack cocaine, where you can directly It's kind of plasticky and yellow, doesn't look good, but when you volatilize that, that can go right across membranes. Okay, so this ability to be soluble in water, right? If you want to take a drug, you want it to dissolve, actually. Things that aren't soluble aren't going to go, are probably just going to pass through your digestive tract. So you want things to be water soluble so you can take them orally, generally, but amines have this great character that they can be deprotonated and then go through membranes. Okay, I want to contrast amines with amides, because when you put a carbonyl group here on an amine, it's not an amine anymore. It's an amide, and that's a completely different functional group. And I want to urge you to resist the temptation to ever use that lone pair to pick up a proton. In this class, I don't think ever in your life you will ever see an amide with a carbonyl attached to a nitrogen that picks up a proton. And let's talk about why that is. It's not that amine lone pairs are not nucleophilic, they are nucleophilic, but they are donating into that carbonyl. So let's go ahead and draw that resonance structure, because this is what the lone pair is doing. It's donating into that carbonyl group in order to give you an alternative resonance structure. And this gives us a clearer picture when we can see both of the resonance depictions. These are the same molecule. It's not an equilibrium. It's the same molecule, just different depictions of the same molecule. And now that we can see in this other resonance form that there's actually a positive charge, a formal positive charge on the nitrogen, and there's no lone pairs, I don't think you would ever be tempted to use that N+ to pick up a proton. There's not even a proton, there's not even a lone pair left on there. So when you mix amides with under acidic conditions, they don't protonate on nitrogen, they protonate on oxygen because of this resonance contributor. So I hope you can see why, when you look at this alternative resonance structure, that's so obvious. So this is the way you protonate an amide on the oxygen atom. And then if I wanted, I could draw the alternative resonance depiction for this. Let me go ahead and use my red pen for that arrow pushing. So amides protonate on carbonyls, never, ever on nitrogen. That carbonyl just completely kills the nucleophilicity and the basicity of that nitrogen lone pair. You'll see a situation reminiscent of this when you look at anilines. Anilines have lone pairs that are donating into the carbonyl group. Let me just, sorry, I wanted to just, okay. So anilines have nitrogen lone pairs that are donating into aromatic rings. And you already know that because we've talked about the effects of amino groups on aromatic rings when you do electrophilic aromatic substitution. Let me draw out one of the resonance contributors, an alternative resonance depiction for an aniline. This is one of the most activated types of aromatic rings, is when you have an amino group on the aromatic ring. And so when I draw this resonance contributor here, this alternative resonance depiction, you can see there's not even a lone pair on that nitrogen in this alternative resonance depiction. There's a positive charge. You would never want to protonate that nitrogen, but it can still happen. Why does it happen? It's because lone pair donation is not so strong that this really reacts like a carbanion. You can still protonate the nitrogen of an aniline. You can still protonate an amino group when it's attached to a benzene ring, but it's 100,000 times less basic than a regular alkylamine. I'm not going to draw every resonance structure. Of course, there's resonance contributors where I can move that carbanion negative charge over to the para position and the other ortho position. But these alternative resonance depictions explain, right? This N+ explains why it's so much harder to protonate an aniline nitrogen. The pK of protonated anilines is about 100,000 times lower than a corresponding alkyl ammonium compound. So this alternative resonance depiction explains the lower basicity of amino groups when they're attached to benzene rings. And boy, they love to ask you questions about this in the book, in standardized exams. It's just like because it requires you to understand resonance and be able to draw fancy resonance depictions of substituted aromatic compounds. So when you go to section 25.10b, they bring up this whole issue of resonance that's kind of reminiscent of the chapter that we had on carboxylic acids and phenols, where you have to draw a lot of resonance structures to explain why phenolate anions, the conjugate bases for phenols, should be stabilized. And so in a similar way, drawing resonance structures will help us to understand the dramatic differences in basicity between anilines that are substituted at the ortho or pair positions by either nitro groups or just an H or a methoxy group. But let's go ahead and take a look at how dramatic those differences in basicity are. These lone pairs are not equally reactive. If we put the right group, either ortho or para, on here, those lone pairs can donate in by resonance, and the nitro group can help stay or help accentuate other resonance contributors where there's no lone pair left on the nitrogen. So, I mean, I'm not really good at math here, but the differences are on the order of about 10 to the 5th or sort of on that order as you switch from a nitro group to a methoxy group. Let's go and draw out some of the resonance to help us understand what's going on there. If you put a nitro group at the pair position of an aniline, it really kills the basicity of that nitrogen lone pair. Right? This is going to have the conjugate. If you put a proton on there, it would really want to get rid of it. Let's take a look at what that lone pair is doing. That lone pair is donating, and I can make the electrons end over here at the ortho position, but I'm going to keep pushing those electrons until I leave them right here next to the nitro group at the pair position. So you have another resonance contributor with this lone pair right next to this N+, and I can keep pushing and draw another resonance contributor where I put the negative charge on oxygen. That's a great resonance contributor. When you can put negative charge on an electronegative atom, and when you see these other resonance contributors, you can see there's an N+. Why would you want to protonate that? And in addition, there's not even a lone pair. So extremely difficult to protonate this type of an aniline compound when you have a nitro group or some sort of resonance acceptor on there, like an acetyl group has a carbonyl. If you put a carbonyl here, you'd also have that same effect where the ability to donate in really stabilizes, or I don't want to use the term stabilization, but really enhances this type of resonance contributor where it looks like N+ with no lone pairs on there. Now the situation is a little bit reversed when you have resonance donors with lone pairs, not resonance acceptors, but resonance donors, either nitrogen with a lone pair or an oxygen with a lone pair. The effect here is that these groups have lone pairs. They don't accept donation. So when I try to draw out some other resonance contributor in the same way that I did for the nitro group, I'm going to end up with this situation where I end up with lone pairs right next to each other, and the lone pairs on the oxygen want to donate into the ring, just like the amino group lone pairs. But if there's carbanion character at that para position, it's kind of stuck. Very frustrating. This is not a very important resonance contributor. So, because you don't really want to have a lone pair right next to a carbanion. So, the nitrogen is not. Let me go ahead and make this. It's not an. I'm not trying to draw an arrow. It's the nitrogen is not very basic. If you put an alkoxy group or an amino group, or sorry, it's not very stabilized. Let me just say, I'll just say it's basic. This is the one that's not basic. I didn't have a term for not very basic, very non-basic. But when we have a lone pair there, man, that lone pair is not donating as much into the benzene ring as if you have a regular aniline. Okay, so this is one of those sections in the book where you have to practice drawing lots of resonance structures to be able to explain the effects of substituents. And go ahead and practice on your own, but if you put one of these substituents at the meta position, doesn't matter whether it's an amino group or a nitro group, you don't see these types of dramatic effects. It's only when they're attached to the ortho and the pair positions that you see the most dramatic effects on the basicity of aniline nitrogen lone pairs. Now, in that section of the book, they introduce a lot of different types of heterocycles and discuss the basicity, but I want to introduce you to a super fundamental principle that relates to the basicity of nitrogen lone pairs. When I see lone pairs on nitrogen, they are not all created equal. I am instantly recognizing the hybridization of the nitrogen atom in those compounds when I see a lone pair on nitrogen. Let's go ahead and talk about how hybridization affects the basicity of lone pairs. So I'm going to take 3 different compounds that have nitrogen with a lone pair, and I want to assign the hybridization of the nitrogen atom in each of these compounds. So over here, if I take methylamine, that's got the nitrogen atom has an sp3 hybridization, that nitrogen atom. If I look over here at an imine, a nitrogen that is part of a double bond, that's going to be sp2 hybridized. And finally, when I come over here to a nitrile, that lone pair is going to be on a nitrogen that is sp hybridized. And the P character correlates incredibly strongly with nucleophilicity and basicity. Let me go ahead and put some numbers on that because it's hard for you to get a sense. You might think, oh, 75% P character, 66% P character, 50% P character, that's not much. How much of a difference could that make? I'm going to put these numbers, the relative basicity of these lone pairs relative to the imine here. And relative to the imine, an alkylamine is about 100,000 times more basic than an imine or any sp2 hybridized lone pair. It doesn't matter whether it's part of a ring, part of an aromatic ring, it's sp2 hybridized. It's way less basic. More P character means more basic. Those lone pairs are more basic and more nucleophilic. And conversely, if I decrease the amount of P character on that nitrogen, that lone pair becomes super non-basic. I'm going to go ahead and put a number here, and I hope I can get all the zeros correct here, but it's going to be, I think, something on the order of maybe 15 orders of magnitude. Does it even matter? Well, I can't even count out 15. It's hard to do that. Well, something. I'll just put a 1 there. Who cares? It is so much less basic. If you have not been paying attention to hybridization since day 1 in this class, I can't imagine how confused you are about the relative reactivity of lone pairs. This is something I think they taught you in one of the early chapters of the book, and then they never mention it again, as though it doesn't matter. But look at the dramatic difference in basicity that you get just by changing the hybridization of that nitrogen atom. Okay, let's take a look at a way to recognize, because nitrogen-containing heterocycles are super important for biology, for the pharmaceutical industry, especially for the pharmaceutical industry and for drugs. And I want you to be able to recognize when a nitrogen lone pair that's part of an aromatic heterocycle, when is that nitrogen going to be basic and when is it not? And here's our general rule, is that if you have a lone pair on nitrogen in one of these types of heterocyclic rings that is attached to a double bond, attached, not part of the double bond, but attached. So here's a nitrogen in this compound called pyrrole, super common heterocycle. You need to know pyrrole. And the nitrogen atom is attached to a double bond on top and attached to a double bond on the bottom. When it's attached, those lone pairs are not basic. And the rationale for why it's not basic is that the lone pairs are donating by resonance. Let me just write not basic. So the nitrogen atom is attached to double bonds. Now let me contrast that with another type of heterocycle like pyridine, where the lone pair and nitrogen are part of the double bond. See that nitrogen-carbon double bond there? The nitrogen is part of a double bond. And that lone pair is a little bit basic. Now, note, it's sp2 hybridized, so it's not like a regular amine, right? That's about 100,000 times less basic than a regular nitrogen, but at least it does have some basicity. So I'll just write a little bit basic. As opposed to this pyrrole, you cannot stick a proton on that nitrogen. If you try to treat pyrrole with acid, it'll protonate on carbon. It's an enamine. So over here, we do have some basicity. It's a little bit basic. And over here this is a cool compound. It's imidazole. It's the side chain of the amino acid histidine. It's got both types of nitrogens. So see over here, there's a nitrogen atom that is not part of a double bond, but it is attached to 2 double bonds, right? That lone pair there is not basic at all. You can't stick a lone pair on that NH group on the N on this N of imidazole. So it's not basic at all. But in contrast, this nitrogen over here that is part of a double bond, that's a little bit basic. So it's a little bit basic. So you should be able to, I expect you to be able to recognize when nitrogens that are part of heterocyclic aromatics, I expect you to be able to recognize whether they're not basic at all or whether they have some basicity, just based on that simple principle. And I expect you to know that more P character means more basic and more nucleophilic, right? Look at the dramatic effect that has. Okay, there's another section in the book that is basically a review of amine nucleophilicity. Amine lone pairs are very nucleophilic, but do not use them for SN2 reactions. Remember, we started off this whole chapter discussion on amines by talking about the problem with trying to do SN2 reactions on amines, and that is you can't control the overalkylation. So that's why we came up with these alternative procedures like the Gabriel synthesis for ways to use nitrogens as nucleophiles. There's another section of the book that describes a weird reaction called the Hoffman elimination. I'm not going to ask you anything about that. Kind of cool for you to read. This was really interesting back in 1851 when it was discovered. But you know what? It's not been interesting since then. I don't know why they put that in the book. I can't conceive that I would ever ask you about that. And it seems like the book is stuck in a time warp by asking you about or introducing you to the Hoffman elimination. We have other fish to fry in this class, in my section of Chemistry 51C. Okay, let's talk about a super important transformation of anilines, of amino-substituted benzene rings. I'm going to introduce you to a reaction of amines, and it doesn't have to be an aromatic amine, but that's where it tends to be used the most, with a compound, a weird acid called nitrous acid. And nitrous acid is kind of like hydrocyanic acid. It's one of these things that you cannot buy because it's not stable. You have to make it in the lab. And just like HCN, you make it by taking a salt, a cheap white powder salt, and mixing it with hydrochloric acid. And under the conditions of the reaction, let me go ahead and draw out the Lewis structure for sodium nitrite. Here's the Lewis structure for sodium nitrite. So when you protonate sodium nitrite, by putting it in under acidic conditions, you generate this unstable acidic species called nitrous acid. And so let's go ahead and talk about what is it that nitrous acid does when you put it into into solution. It's unstable because when you put nitrous acid into solution, let me go ahead and draw out an arrow pushing mechanism for this. It protonates. It protonates everywhere. It protonates on the hydroxy, on the nitrogen lone pair, on the oxygen lone pair. It probably protonates fastest on the double bond O oxygen and the double bond N nitrogen. But that doesn't explain why it's unstable. If you want to explain why it's unstable, we have to do something which seems kind of crazy, which is put the proton on the hydroxy group. This is not the most basic atom on here, but as soon as you protonate that hydroxy group on nitrous acid, it now is ready to push water out as a leaving group. And so now we're in this situation where we're set up with a lone pair here that can just bend right on over and push out water as a leaving group. And this generates this very strange species that you have never seen before called a nitrosonium ion. Let me go ahead and draw out that nitrosonium ion that you generate. I hope if you kind of squint your eyes that you'll see this looks a little bit like an acylium ion. It's kind of the same principle. So let me go ahead and finish drawing out just so you can see how the Lewis structure fits together. If this were one of these arrow pushing mechanisms, there's no reason to draw those lone pairs for a sapling exam. So this is what's happening in solution when you generate nitrous acid under acidic conditions. There's a small equilibrium amount of this very weird species called a nitrosonium ion. Sometimes people write out nitrous acid, they write HONO. That's not an acronym, they're just trying to use a typewriter keyboard to write out the chemical structure of nitrous acid. But again, you can't buy that. You have to make that in the lab. You mix sodium nitrite and hydrochloric acid, or you could use another strong acid, and it generates small amounts of this nitrosonium ion. And what does that nitrosonium ion do? It reacts with amines. Let's go ahead and take an example. It could be an aromatic amine, it could be an aliphatic amine, and unfortunately, it can also be the amine groups on your DNA bases. That's a problem. And so here I'm going to draw an amine. We don't really care that much about what the R groups could be. It could be an aryl group, even though aryl amines are not as reactive as regular aliphatic amines. These nitrosonium ions are so reactive. Again, I hope this nitrosonium ion looks kind of freaky to you. You've never seen anything like that before. So if it looks freaky, okay, I understand why. So let's go ahead and attack that. Don't attack the O with the positive charge. It's already got an octet of electrons. Please don't add another bond to that. It's not going to remove the positive charge. Okay, so you get this species now that has a nitrogen-nitrogen bond. And now we have this group called a nitroso group. And this ammonium is going to be deprotonated by the conjugate base that's left over in solution. Let me go ahead and draw that conjugate base. Here we go. And then when you deprotonate this, the intermediate that you get is an N-nitrosoamine. And you can isolate these. If you take piperidine or dimethylamine or some aliphatic amine, you can isolate N-nitrosoamines. These are, unfortunately, they tend to be carcinogenic. I'll just write the word carcinogen. So you want to stay away from N-nitroso compounds because they have the capacity through additional types of reactions to alkylate DNA. And if you outpace the DNA repair mechanisms inside of human cells, that can end up leading to cancer. But this turns out to be a useful reaction in the laboratory and inside of your flask. Your flask isn't going to get cancer. So if you take sodium nitrite and you add hydrochloric acid to an arylamine, an aniline, that's going to generate the same type of an N-nitroso compound, but that will keep going. Let me go ahead and draw out that what's happening with an arylamine. I'm not going to redraw the mechanism for formation of an N-nitroso compound with aniline. It's the same mechanism that I just showed you, so I'm going to start with that N-nitroso compound. So you end up with, initially you end up with an N-nitroso intermediate, an N-nitroso aniline, and this keeps going under the acidic conditions. Right, as long as the conditions are acidic, this will keep on reacting. So let me show what happens as this reacts with acid. I'll go ahead and make this lone pair on the oxygen atom, pick up a proton. And I kind of regret that earlier in this course, I sometimes drew multiple lone pairs. And then on the online exams, I say, don't draw any more than one lone pair. Sometimes 0, but don't draw more than, you don't ever need more than one lone pair when you're drawing an arrow pushing step. Sometimes you need 0 if you're doing an SN1 ionization. And most of the time you're starting with one lone pair for arrow pushing steps. I'll go ahead and draw this next intermediate. And so here's the protonated N-nitroso compound. That's a oxonium ion, the oxygen with 3 bonds. Sure wish that I had drawn that bond to this H more carefully because I need to break that bond. We're going to deprotonate this. We generate a conjugate base from this process that's got a lone pair on it. And we're going to deprotonate and push these electrons over so that we satisfy that positive charge. And now, because we're under acidic conditions, this can protonate. And it protonates on the nitrogen lone pairs, this other nitrogen lone pair, but sometimes it protonates on oxygen. So let me go ahead and draw that. I'll draw the acid, this symbolic acid that we generate. Again, I'll just draw one lone pair. That's all we need here. And we'll show that we can pick up a proton on this hydroxy group and generate a leaving group. And now we have a water leaving group attached to our azo compound, our azo species. And so there's lone pairs that are anti to that water group, that water leaving group, and that gets pushed out. You could make the lone pair end here in the middle of the double bond, or you can make it attack the nitrogen. Either way, just be very clear when you depict things and you draw things like that. And so this ends up leading to something called a benzene diazonium ion. And that's this species over here. It's a weird looking species that you've never seen before. And the thing that you need to remember is that benzene diazonium, or I might call them aryl diazonium, because that means it can be any kind of aryl group, want to be attacked. Not on N+, but on the other nitrogen. Don't attack the N+. That nitrogen in the middle already has 8 electrons. It's got an octet. You want to attack the end nitrogen and push the electrons to the N+. So these benzene diazonium ions tend to be very useful. So we're going to show you a whole series of reactions that you can do with benzene diazonium ions. And the way this works, typically, synthetically, when you're trying to make substituted benzene rings, is you take a benzene ring through a multi-step sequence, turn it into a benzene diazonium, and then you can substitute that with some secret recipes that I'm going to show you in a minute. So how do you put a nitrogen atom on a benzene ring? You already know that. That's exactly how we started off this course. We showed you a recipe for attaching nitrogen atoms to benzene rings, and that's electrophilic aromatic substitution. So recall that the recipe is nitric acid for nitration, and then we need an acid catalyst, sulfuric acid. And then step 2, we want to reduce that nitro group down to an aniline, like I've shown you up above here. What's our conditions for that? Well, in most cases, you can just use hydrogen and palladium on carbon. And if you've got some sort of halogen you don't want to hydrogenate off, then in those cases you can use tin and hydrochloric acid. So this generates an aniline, an aminobenzene. It's an aniline. And I just showed you the recipe now for converting that into a diazonium ion. You take sodium nitrite, NaNO2, and hydrochloric acid, and that'll generate a solution of this benzene diazonium chloride salt. So don't forget the chloride. If I draw a box, remember on my exams, let's suppose I draw a box and I say draw the product in the box. You have to draw that counter ion there because there's no such thing as just a flask full of positively charged species. It has to be a counter ion there. Okay, so boy, when you see a benzene diazonium ion, I hope you can see that it contains a nitrogen molecule. And this thing would really love to lose nitrogen to generate nitrogen gas because nitrogen gas is so unstable. But I have to caution you, even though this thing wants to release nitrogen gas, the carbocation that you would generate, actually it's a type of carbenium ion, is so unstable, so unthinkably unstable that it doesn't lose nitrogen gas through this kind of a mechanism. It's just, this type of a carbocation is completely unstabilized, and even worse because it's sp2 hybridized. It's less stable than an regular carbocation. Let me just remind you why the double bonds on this ring cannot possibly stabilize this empty orbital through resonance. That's because the electrons that are in this benzene ring are in pi-like orbitals. They spend their time, let me draw one 1p component of a pi-like orbital. They've got electron density above and below the plane of the ring. They have absolutely 0 electron density in the pi bonds in the plane of the ring. And that's exactly where the empty orbital is. There is no possible way, even if it wanted to, that these pi electrons, which spend 0 time in the plane of the ring, can ever overlap and donate into that empty p orbital. So this would be the worst type of carbocation you could imagine. You never see this loss of nitrogen gas through the mechanism that I'm showing you there, at least at normal temperatures. You know, who knows what would happen if you heated this to 200 degrees, but we don't do that. It would probably explode or something. So don't try to do SN1 or SN2 reactions with benzene diazonium salts. I'm going to give you a series of recipes that you can use these for that turn out to be extremely useful. Because when we showed you electrophilic aromatic substitution, we showed you how to make carbon-halogen bonds, put them on a benzene ring. We showed you how to make carbon-nitrogen bonds with nitration. We showed you how to do Friedel-Crafts acylations and make carbon-carbon bonds to benzene rings. We showed you how to make carbon-sulfur bonds with sulfonation reactions. But there's plenty of groups we did not show you how to put onto benzene rings. And those turn out to be super important for modern drug and pharmaceutical synthesis. I'm going to take you back about over a century to the origins of the field of organic synthesis. And that is the dye industry. All of the major chemical companies and the pharmaceutical companies, the #1 chemical company in the world, BASF, started off as an aniline dye company. Badische Aniline and Zollefabrik was a German dye company that made their business just like the other major chemical industry companies. They started off by taking anilines and making diazonium ions and then using them as electrophiles in electrophilic aromatic substitution. And when you end up with these species that have benzene ring and then this azo group, let me go ahead and label that so you know, so we have a name for this thing. This species is called an azo group. Benzene ring, azo group, benzene ring, those are azo dyes. They have all kinds of colors. Brilliant reds, brilliant blues, yellows. Whenever you drink Kool-Aid or some soda that's brightly colored, almost always it's an azo dye. So let's go ahead and take a look at what's going on here. This is nothing more than an electrophilic aromatic substitution. What we're doing here is that we're simply substituting this. We're replacing an H here on a, let me go ahead and draw the reactant. You're simply replacing an H on a benzene ring with a new substituent. And so the starting material that you would use for this would just be some activated aromatic compound. And this would obey all the other rules that we told you about electrophilic aromatic substitution. Like if you have two groups on an arene ring, the strongest activator controls the regiochemistry. That's the hydroxy group. And so the hydroxy group would lead to substitution, either ortho or para, but the para position is blocked, and so the electrophile would go to the ortho position. We'll talk more about that shortly, or when we come back on Friday. Here's 4 other extremely useful recipes that you could do with arene diazonium ions. And I'm putting some random substituents on here to make it look more interesting. Right? You should know how to make an arene diazonium. If you start off with toluene, you do a nitration, you reduce it to an amino group, you do that nitrous acid trick to make the arene diazonium ion. If you want to replace this with an OH, and I'm not going to tell you the full recipe, I'm not going to tell you the mechanism, I'm simply going to tell you that if you treat this with water, and I'm not, again, there's more to these conditions, that you can replace diazonium groups with hydroxy groups. It's not SN2, it's not SN1, don't worry about that. And this turns out to be powerful. We haven't shown you any other way to put oxygen atoms onto benzene rings. This is the only way you can do it in this class, is to make a benzene diazonium and then treat it with water. And in this case, it's got a chloride counterion. Let's take a look at another powerful reaction that you can do with benzene or arene diazonium ions. We can replace those with fluorine, and you can't do this with F2 and Fe, F3. There's that iron trick that we showed you for bromination and chlorination of benzene rings doesn't work for fluorine. And this turns out to be a super important substituent for modern pharmaceutical synthesis. And the recipe we use is a species called fluoroboric acid. I'm going to show you the chemical formula, HBF4. Like, what is that stuff? Well, imagine taking boron trifluoride, this is a common Lewis acid we use in our lab, and mixing that with hydrofluoric acid. And what you would end up getting in that case is this. The HF would form a bond to the boron, but eventually you would end up with something that you can imagine, something like that. There's actually an HF bond there, so it's not like the H plus ever exists. That's making me uncomfortable. Let me draw it with the correct structure here. Be F plus and B. So you can imagine how much F hates being F plus. That's a strong acid. And we're not going to talk about the mechanism. These are just recipes for you. Don't worry about the mechanism, but you can substitute diazonium ions with fluorine. We also did not show you how to make carbon iodine bonds. We showed you how to make carbon bromine bonds on arene rings. We showed you how to make carbon chlorine bonds on benzene rings. And if you want to make a carbon iodine bond, you have to mix these diazonium ions with potassium iodide. Can't use FeI3 and I2, it does not work. So these turn out to be super important substituents to be able to put onto benzene rings, fluorines and halogens. And so, again, if you just wanted a chlorine atom on a benzene ring, we already showed you the recipe for that. I think on the first day of this class. The last secret recipe we're showing you for putting substituents directly onto benzene rings is to replace a diazonium group with a cyano group, with a CN triple bond. Once you do that, you can add Grignard reagents or hydrolyze it to a carboxylic acid. But our secret recipe in this case is cuprous cyanide, copper cyanide. And you don't need to know the mechanism. Don't worry about the mechanisms for these reactions. I'm not going to ask you about the mechanism. I'm not even comfortable showing you the mechanism for these at the level that you're at right now. But the transformations themselves are super useful in the, for pharmaceutical synthesis because these substituents appear quite frequently in drugs or in along synthetic routes leading to pharmaceuticals. We are circling back to a concept that was originally introduced at the start of this course, and that's the concept of electrophilic aromatic substitution. I just introduced to you arene diazonium ions, phenyl diazonium ions. And let's go ahead and take a look at this coupling reaction that I mentioned that was so important in the birth of the organic chemistry industry, of the chemical industry, through the generation of azo dyes. So I'm going to go ahead and draw out a phenyl diazonium ion. Remember, these are generated with nitrous acid, and so they'll always be generated in this course as diazonium chloride salts. And these are electrophiles for electrophilic aromatic substitution. And the electrophilic atom is not the nitrogen with the plus. It is the nitrogen over here on the end. So I'm going to highlight that. That's where you want to attack. And then you'll push the electrons to the N+. So when you treat this with an activated arene ring, those are typically phenols, anilines. I'm going to give you an example of a dihydroxybenzene compound called a resorcinol. And you'll note that both of these hydroxy groups are ortho paradirectors. We're not going to substitute in between those. The preferred site of attack in this case is going to be ortho to one of the hydroxys and para to the other. So these electrons are going to be reactive in electrophilic aromatic substitution. And so when we draw out this reaction, the arrow pushing is going to look just like all the other arrow pushing reactions for electrophilic aromatic substitution. We're going to attack the nitrogen, and then we're going to push the electrons over to the end that has the plus. Don't attack the N+. It already has an octet of electrons. The product of this reaction, let me go ahead and draw out the final product, and then I'll draw the mechanistic intermediates. The final product of this reaction is so heavily conjugated. These types of compounds where you have what's called an azo linkage between two arene rings, those have very high levels of conjugation and tend to be deeply colored. I'm not sure if I have enough room to fit these hydroxy groups in here, but let me go ahead and try to do this. So we're adding ortho to one of the hydroxys and para to the other hydroxy group. So the mechanism for this is like any other. We're going to generate an arenium ion intermediate. Let me go ahead and draw out those mechanistic intermediates, or the key mechanistic intermediate. And so once we push the electrons over to that nitrogen, we're going to generate this arenium ion. And I'll go ahead and draw that key proton that's there on the arenium ion. Really wants to regain aromaticity. And floating around somewhere in solution, we're going to have chloride or water that we don't need to worry about the fact that the identity of the species that's pulling off that proton. There's so many species present. So I'm simply going to acknowledge the fact that these reactions are run under acidic conditions, right? This is the same reaction mixture that had the nitrous acid in there. And now we'll go ahead and show the deprotonation of that arenium ion in order to regenerate aromaticity. What a super important reaction for the development of organic synthesis. All the major chemical companies and pharmaceutical companies had their origins in German dye companies that specialized in making highly colored compounds through this key electrophilic aromatic substitution reaction. You know, I hope that this looks similar to you. This should look very similar to the reaction of acylium ions. So I hope it's not unusual in any way, because you've already seen a lot of reactions that involve these acylium ion species. And remember, when we did electrophilic aromatic substitution with these types of acylium ions, we saw these effects where, I'll go ahead and draw one of the OR groups, where aromatic rings, especially an activated aromatic ring with an alkoxy group, can easily attack. We don't attack the O+, we attack the carbon atom, and then we push the electrons to the O+. So this is similar to these reactions of acylium ions, so I hope it won't be a mystery. But what a powerful reaction. It's just great to bring us back to the very beginning of the course where we talked about electrophilic aromatic substitution and the origins of the organic chemistry industry. So section 25.16 is an elaboration of synthetic dye synthesis. That chemistry is really kind of 120 years old, longer actually. So I'm not going to ask you any of the stuff in that section, but it's kind of interesting to go back and look at the reactions that are so important to the birth of organic chemistry. There's another section in chapter 25 on the synthesis of sulfa drugs. And again, these are maybe 60 or 70 years old. They're nothing like the modern pharmaceuticals that we use as antibiotics. So I'm not going to be asking you about that really ancient chemistry. But I do expect you to know this electrophilic aromatic substitution reaction, just like the other 5 classes of electrophilic aromatic substitutions that we learned at the beginning of the course. This is kind of a 6th category for forming carbon-nitrogen bonds off of benzene rings. Okay, that's the end of the new material for our Chemistry 51C series. The next few lectures, we're going to be reviewing the material for this course, just walking back as much as we can, as much as we have time for the material. I encourage you to go out, solve problems, practice problems in the book, practice problems in the online homework system, stay connected, go to discussion section, be interactive, and stay sane and stay healthy.